Hi, welcome to an Arduino tutorial from Robojax. My name is Ahmad Shamshiri. In this tutorial, I'm going to show you how we can use this medical accuracy, long-range infrared contact lens, temperature sensor MLX90614. This is the DCI version with a field of view of 5 degrees where you can measure up to 50 centimeters with very high accuracy, where the length of the object will be about 4.3 centimeters. This tutorial that I'm presenting, the code and wiring will work for the module that is sold like this, the bare module without any PCB, or this module, or if you get it like this. I'm going to explain the module. I'm going to show you how to prepare this with capacitor and wiring. Then I'm going to explain the code, and then I'm going to demonstrate it at different distances up to 50 centimeters. You can get the code for this by clicking at the link below the video in the description, which will take you to robojax.com/learn/Arduino. Let's get started with this. This is the Melexis MLX90614 in this format, TO39. This is the DCI version, which has a field of view of 5 degrees, the narrowest in this family. This is the medical accuracy version, the most expensive one. I've written a specific code for this so we can compensate the power supply dependency of this, because this is the medical accuracy version, and we will get very accurate. And also the coating on the lens here, it has the gradient compensation applied to this, so we are getting very accurate reading up to 49 centimeters. I have a separate video explaining the shorter version of this. I've purchased this from AliExpress from this store, iWink001, and you can get it from any other store. I have no affiliation with this. And if you select this version, it shows $41.58. This shows $3.26 for the shipping, which you get it in 60 business days, but you can select a faster method, and I paid about $21 shipping to get it faster. I have $6 version as well, and the other versions. I'm using SketchUp online to demonstrate this. If this is your sensor and you're pointing it to the surface, this is a circle that is covered by the infrared. You will measure this circle, and here from the sensor, when it hits the surface, we are creating a triangle here from the surface to the point where the infrared hits. So this is the area we are measuring. And if we flip it, then this is our triangle. This is the length from the sensor to the object, and we want to find out the area and this diameter of the length if you want to know it. If you look here, because this is 5 degrees, the length is, and this is actually this distance is this distance, the D. L is the radius of the circle, and this is 2.5 degrees. I've just made it so large so you can view it, and this is 2.5. So we are measuring this length, and this is the radius of the circle, which is one side of the triangle, the opposite side. This is the length of the object, 2L, twice as this, including this portion. That is the length of the object, and that L is tangent of 2.5 times D. Then if you look at the circle that is at that point, the L is that radius of the circle. And if you want to find out the area of the beam, area is equal pi L squared. And then we have one formula here now. And if you want to know the length of the object, it would be 2L. L is the opposite side of the triangle. And if you want to get just the L, it's tangent of 2.5 times D. This is our formula. And here I've created this sheet for the distance from 1 centimeter even up to 50 centimeter. and the length of the object that you can measure from at 1 centimeter it will be 0.1 or 1 millimeter, which it cannot do it because it will be too close. And as you can see, at 50 centimeter we are getting 4.3 centimeter, which is very reasonable. To understand the 4.3 centimeter, that's 4 and that's 4.5. So we are measuring an object at this size. So the average of the temperature will be very acceptable, because human body will have almost the same temperature from this point to this point on the face or other part of the body. And if you want to know in terms of circle and area, so in terms of length, 4.3 centimeter at 49 centimeter, that's the length of the object, and in terms of area it will be 14.38 centimeter squared. We are using the TO39 package, and they come with two range. One is from -40 to 125 degrees Celsius, and the other is from -70 to 380. So we can determine the type from this chart, and this is the one that I'm using, and that is ESF DCI. After the MLX90614 we have ESF and then DCI, and this is the version where it says also ESF, because we are using the ESF, and here after this number we have E and then SF. SF refers to TO39, so this is the package type, and E is from -40 to 85, and as you can see K is -40 to 125. So we are using the E, which is -40 to 85, and after this we have DCI, and as you can see here, D is the 3 volts medical accuracy. The previous version we had was the A, which was working with 5 volts, but this is with medical accuracy, so this is way accurate. And then CI, the second digit is C, gradient compensated, so it is compensating internally for the gradient temperature reading. And then I, the third one, when you look at the I is 5 degrees field of view, and as you can see amongst all of these, this is the narrowest field of view with highest accuracy. I had another video explaining this BAA version where the field of view was 70 degrees. This was very wide and inaccurate, and now we are going to test the DCI version, which has a field of view of 5 degrees. Let's talk about the field of view, or FOV. For each of these temperature sensors with infrared, the field of view is the sensitivity where we receive the signal at 50%. And for each device we have different sensitivity. For example, this is a device, and when it hits a point of heat source with different type, we have devices which has AA, BA, CC, CF, CH, and then CI and CK. The version that we are working is this CI, and field of view is, as you can see, 5 degrees, which is very accurate. I had a video a while ago, and the field of view for that one is 70 degrees, and also we even have 90 degrees. When it is 90 degrees, you're almost reading nothing. It will be very, very inaccurate, and you need to be almost in direct contact. When you make the field of view narrow, then you have very longer range. For different version, here they show, as you can see from here, it's about 45 degrees on this side and 45 degrees on this side, so total is 90 degrees. And then we have BA, the one that has dual zone, so we get some field of view on this side, on one channel the red, and then we have from the other channel, and if we combine it together, then this is the field of view that we are getting. Then we have CC version. As you can see, this is around 15 degrees on this side, 15 degrees, total will be 30 degrees field of view. CF version, CH version, then the CI version, or the one that has D but then CI. The CI version, there are two types, so this is 2.5 degrees on this side, 2.5 on this side, and we are getting 5 degrees field of view, but that's one characteristics that increases the sensitivity, but the one that we have is D with medical accuracy. Medical accuracy, this is the object temperature and this is the ambient temperature. So this versus the object versus ambient, as you can see, from 22 degrees to 36 degrees it's plus minus 0.3 degrees Celsius, and as soon as you go from 36 to 38, which is the human body temperature, it's plus minus 0.2 degrees, which is very accurate. But you cannot achieve this accuracy without some consideration that has been mentioned in this device. So temperature reading dependency on VDD, that's a power supply, and this device, the accuracy will be increased if this is considered. So we have a typical VDD dependency of ambient and object temperature is 0.6 degrees Celsius per volt. So we have to consider this in our code in order to get very accurate reading. It shows the temperature error with respect to the voltage. See here, this is for the ambient temperature. As the temperature deviates from 3 and it is being reduced to 2.2 or it increased to 3.8, this relationship is, as you can see, this is the error. So we are deviating up to 0.4 degrees Celsius positive or 0.4 degrees Celsius in the negative side. And this is the typical object temperature dependency on the supply voltage. As you can see, again, this is not flat and it deviates from the value. This is 0 and 0.1, 0.3 and up to 0.4 to the positive and negative. So it fluctuates up and down as the voltage changes. So we have to do something, and here this is a formula that we are using. It says that the compensated temperature is the object temperature minus VDD, that's a power supply, VD naught, times typical dependency. So in a simplified version of this is that object temperature minus VDD, this is a supply voltage where we are going to use 3.3 volts, minus 3 volts times minus 3, that's a voltage, times 0.6. And we are going to practically read the supply voltage and measure it and then subtract this so we can get very accurate and multiply it by this 0.6 degrees Celsius per factor. And here, and the result will be almost flat curve. As you can see, it will be increases or decreases. We are getting almost flat line. And here, when we are using it directly without a PCB, in any of these versions, either with AAA or the other version, we need to connect a capacitor between the ground VSS and the supply voltage VDD, a 0.1 microfarad or 100 nanofarad ceramic capacitor, in order to reduce the noise. And here is a wiring diagram for the PCB version. If you have this PCB, the last pin is labeled as SDA. It has been connected to analog 4. You can also connect it to SDA in here. SCL is connected to analog 5. So these are I2C communication pins. Then we have ground. Ground is connected to one of the grounds. And then VN. VN is connected to 3.3 volts. And from this ground, one more wire is needed, and it's a must. Bring it to analog 0. And here are for the pins. If I hold it up, this notch, this piece that you see here, this one, so we know this is VSS, that's a ground, and as you can see, this is attached to this piece of body. And this pin on this side, that is a power supply, the ground in here. And this pin on this side is SCL, and this is SDA. We are going to use the I2C communication to connect this to Arduino to read temperature. Between power supply and ground, we have to connect a 0.1 microfarad or 100 nanofarad capacitor. This is a ceramic capacitor. And here, let me show you so you can see it larger. It says 104. That 4 means 4 zeros. And here is how you attach 100 nanofarad ceramic capacitor between the pin. Pay attention to this notch between this pin, the ground, and then the VCC. And here I've soldered the capacitor between this pin, and also I've soldered all these wires, and these are the heat shrink that I'm gonna put so they do not get short-circuited. This is the 3.3 volts. This goes to 3.3 volts. This goes to 3.3 volts this side, but we have connected this wire here where this will go to analog 0. So we are reading the voltage from the 3.3 volts to analog 0, so we can do that. So we can do the compensation for the power supply dependency. And here the wiring is completed. I have soldered 4 wires. The red and black are my 3.3 volts and ground. Here the blue is SDA and this is SCL. And if you're using just a bare module, pay attention to this notch. This pin is connected to the ground using the wire that I've labeled black, and then this is connected to SCL to analog 5, and the second one, this is SDA, this is connected to analog 4. And here this is a power supply or VCC. On the module it's VDD, so this is connected to 3.3 volts, and also from this point solder one more wire to analog 0 where we will be reading the 3.3 volt voltage as it fluctuates, goes up and down because it's not precise, so we must have this for precision. If you want to learn Arduino, I have a bestseller course on Udemy where you can learn Arduino from ground up with hundreds of projects, all course material, library, codes, wiring diagram, everything available in one place. The link for my Arduino course is below this video in the description. And here let me explain the code. Click on Sketch, include library, and then click Manage Library. Wait for this bar to complete, and here type MLX90614 and press enter. You will see this from Adafruit. This is the one that I've used. You will see install here. In my case it's already installed, so this is great. Click and wait for this to complete and it will be done. We are defining a pin where we will be reading the voltage so we can compensate the voltage dependency of the measurement. In this case I'm using analog 0, so you will type the pin that you're measuring the voltage and enter here the voltage of your Arduino. If you're using an Arduino with 3.3 volts, type here 3.3, and if it is 5, type 5. Is very important. That is used for calculation, not for actual operation. And this wire is part of the I2C communication. This is the library that you just included, and this array of character type is holding the text, ambient, and object. If you want to change it, make sure to keep this double quotation and put other text that you want. And here we are creating an instance of the class and we call it MLX with this constructor, and these are the variables: object C and object F, and then ambient C for Celsius, Fahrenheit, and Kelvin. I've defined all these variables. Here we are initializing the serial monitor with 9600 baud, and this is just a text. This 9600, if I click on Open Serial Monitor or click on Tools Serial Monitor, this is the text that is currently being shown, and on the right side, on the section and the lower right side, it says 9600, and it must match this number, otherwise you will not be able to see the text and serial monitor. And then from the object that we created, MLX.begin, will initialize the sensor. Inside the loop we use print temperature inside single quotation C. It will print the temperature, and if you, after C we use D for the ambient, so this was because for the next letter. And if you want Fahrenheit, put Fahrenheit, that's for the object, and then after F, G is for ambient for Fahrenheit, and the same way Kelvin, that's for the object, and this is for the ambient. After K is L. So you use this to print the temperature on serial monitor, this one. If you want to get the temperature and do something, here F, get temperature, and inside single quotation C, and you want to see if the temperature is greater than 40 degrees or some numbers, then between this opening and closing parenthesis, do something, your code will be here. Now we have written two functions. This is print temperature and this is get temperature. And then between the readings we have 1 second delay or 1000 milliseconds. And here inside this get temperature we define a variable called value, and here we get the temperature, read temperature Celsius. This reads the temperature Celsius from this object that's included with the library, and the result of this calculation is stored in object Celsius, and this is the ambient Celsius, and this is for Fahrenheit object and Fahrenheit for the ambient. And then we do dependency compensation. This is a function which I'm going to explain. So this reads it, and from there we will do the calculation for the rest of the values. If you want a value in Fahrenheit, then we get the Fahrenheit, we set the value to Fahrenheit object, and after F we have G, so it's ambient of F to V. And then if it's Kelvin, then we get Celsius and add this value, it becomes Kelvin for the object, and we set the value to that. After K we have L, it will be Celsius of ambient plus this value would be for the ambient. And if it is C, then we return C to this, I set that one, and if it is after C it's D, so this will be ambient and C, and we set the value and we return it. So this will return this function, dependency compensation. I've used this formula which I've taken from page 37 of the data sheet. We are reading the object temperature and then subtracting this value, and this value 0.6 is a 0.6 degrees Celsius per volt compensation, multiplying it by VCC. This is the 3.3 volts pen, whatever is the voltage, and we are subtracting 3 from it, so this is making it very precise, and the result of this calculation will be our object temperature. Inside the function we are reading using analog read. We are using the pen that we have connected the VCC, which we have defined at the top of the code, and the result of this, which is in 10-bit system, it is between 0 to 1023 and will be stored in here. And then the value that we have read from the pen will be used here, multiplied by Arduino voltage divided by 1023. So this is, if yours is 3.3 volts, doesn't matter. So whatever is the value, this factor multiplied by this value will give you the voltage. So now we have the voltage of the input, and here we are getting the object temperature in Celsius, applying this factor, the voltage that we have used here, and the same way we use that for the ambient, the same way we use it for Fahrenheit. So this will do the calculation and update this value. So now the new value will have the compensated value, and the same way for object in Celsius, object in Fahrenheit, ambient, and this is also ambient, and object for Kelvin and ambient for Kelvin. And this is printing temperature. You get the temperature when you type CK Kelvin or Fahrenheit, that character comes here, and we pass it to this function which I just explained it above. The result of the calculation will be temp or temperature, and then we check if type request is equal C, then we print this text, the name, space, and then the temperature, this temperature, and then we print the degrees. So let me show you this degree here, the degree symbol, and then we print the capital C here. And if it is D, then we print ambient, that's the name, because 0 type name, this is the object, name, and that's the ambient title, and the same way for Fahrenheit, Kelvin. All of this will be printed on the screen. Now let me demonstrate it. Now I put the sensor here on the box so it is above the ground, and I'm putting here a ruler. Now this is located exactly at 0, and now this is 10 degrees, 10 centimeter. I'm holding my hand, and as you can see, it is reading 35.3 degrees Celsius. And let me go 5 centimeter, 35.39 and 47. At 5 centimeter, it measures the length of an object with 4 millimeters. So now at 5 centimeter, it measures at 4 millimeter object. So it is measuring a very small area. So let me go to 10 centimeter here. Now I'm at 10 centimeter. I just put my hand proper at the same level. As you can see, we are reading 35.25. Now let me go to 20 centimeter. This is now 20 centimeter here, the pen, the tip of the pen. Now at 20 centimeter, it is looking at 1.7 centimeter or 17 millimeter object. It's very accurate. Let me go to 30 centimeter. Now I'm at 30 centimeter. But at 30 centimeter, we are looking at 2.6 centimeter or 26 millimeter object. I'm now going to 40, so I have to move this away. Now this is 38, and I'm going 2 centimeter, so this is 40 centimeter. And this is now 40 centimeter, 34.19. That's amazing. So at this point, if I bring my hand, so pay attention, it's 34.25 here. And if I go 20, so 34.57, so it's 0 point some degrees Celsius. And if I go 10, now it increased to 35. And now here I put this ruler, which is 30 millimeter, 30 centimeter at this point, and the other tip is 0. So I'm going to put my hand at 50 centimeter. And because it is pointing up, I have to make sure my hand is there. And this is what we are reading, 34.25. And here at 49 centimeter, we are looking at an object of 4.3 centimeter or 43 millimeter, and the area is 14.3 centimeter squared. Of course, you will not use it for 50 centimeter, but 20 centimeter is very accurate. Now I'm holding my hand here at 20 centimeter, and we are reading 34.8 or 34.77. So that is 20, and let's go 10. $35.19, so 35.29 at 10 centimeter. So proportionally, you can compensate and understand Thank you for watching a tutorial from Robojax. If you learned something and found this useful, please thumb up, as this will help my video in the search algorithm of YouTube. If you have comment or question, please post it in the comment section below. I try to answer and reply. And to get updates of my upcoming videos, make sure to subscribe. In this tutorial, we are going to learn how we can use this touchless infrared temperature sensor MLX90614 to measure the temperature without touching and display it on the screen, either as Fahrenheit, Celsius, Kelvin for ambient and for the object temperature, or on this larger LCD 2004.